And I think we can get started now. Welcome, everybody. This is the third webinar in our series of human factors in aerospace webinars that we're running through the HFES Aerospace Technical Group. Today, we have the privilege of having Dr. Gernot Konrad here to talk to us. Dr. Konrad is the Chief Engineer for Human Factors at Honeywell Aerospace Technologies, and he also has over 22 years of experience designing and certifying highly integrated flight decks. He's here to talk to us today about human factors engineering for integrated flight systems, and I'll let him introduce himself.
Well, okay. Thank you for the introduction. Yeah, some of you may wonder why there are slides in the background say Kansas University. Well, the reason for that is I have developed a human factors engineering course together with Kansas University. And the webinar, the slides which I'm presenting here today are actually borrowed from that Kansas University short course, which I have developed. And that's why it says here the logo of Kansas University. We can get started whenever you want to. I just turn off my camera and I can get started.
Sure, I'll just say for everybody in the audience, wait until Dr. Konrad is done presenting, write your questions down, and then we'll have a Q&A after that. So, Dr. Konrad, take it away.
Okay, great. Thank you very much. And again, thank you for Human Factors and Ergonomics Society for inviting me for today's webinar. The topic of today will be human factors engineering for integrated flight deck systems from ideation via maturation to certification. I would like to start off with this slide here, and you see a lot of the buzzwords which are commonly used around human factors. When we talk about human factors, we hear people talking about human performance, about engineering psychology. We hear them talking about human-machine interface, situation complexity. But what does all this mean? How does all this get together in one discipline? So there is a definition of human factors. I would like to start with a very classic one, ergonomics, which comes from the two Greek words ergon, which stands for work, and nomos, which stands for the natural laws. So ergonomics can be seen as the science of work. However, when this terminology was originally defined, the focus was more on the classic aspects of what we see today as human factors. So the focus was really mostly on physical and physiological properties of the human operator. And there was not so much attention given to psychological and cognitive capabilities and limitations. Today's understanding of human factors does include not only the classic ergonomic aspects, but also considers psychological and cognitive properties of the human operator. So when you go on the internet and you Google for a definition of human factors, you will probably find immediately 100 different definitions. Some are better, some are not so good. I chose here the definition from the Human Factors and Ergonomics Society, HFES, and it's actually a really good one. I'm not reading it to you now, but there are a couple of things in there which I really like. First of all, it recognizes that human factors is a scientific discipline. And indeed it is. We are using methods, we are using a lot of standards, we are going back to literature. It is not just opinioneering or common sense. It really goes way beyond and above that. And this definition also recognizes that it has to do with the interaction among humans and other elements of the system. It recognizes that it's a profession that applies theory, principles, data, and other methods to design, to optimize human well-being and the overall system performance. And I will come back to this term, overall system performance, later in the presentation. Human factors is not only found in aviation. Actually, there are many industries or disciplines out there where human factors is very well established. Think about the nuclear industry, the automotive industry, or all of us, we are using consumer electronics. Of course, human factors plays a very important role there as well. In today's webinar, I would like to focus on human factors in aviation. And even in aviation, human factors can be applied very broadly. You will find human factors at universities where people do research with respect to human factors, and of course, the big and important area of education. We will have the regulators, the certification authorities around the world, which do rulemaking. We have accident investigators, which have to consider human factors aspects when they want to go to the root cause of why an accident really happened. We have maintenance organizations, we have air traffic control, we have training organizations, we have the operators like the airlines out there who operate the aircraft, and then we have the design and production organizations, those companies that actually produce the systems and the equipment and the entire aircraft that is later operated. And again, in this webinar, I would like to focus on the design and production aspects in human factors. Even in aircraft design and production, we can split it up in several areas. Again, we have maintainability, we have human factors in the cabin design. Think about the emergency egress, for example, or think about even the in-flight entertainment system. All these are used by humans, and therefore human factors plays an important role. Writing the aircraft flight manuals, normal checklists, abnormal and emergency checklists, all this involves human factors. In this webinar, however, we will focus on flight deck design, human factors aspects specific to flight deck design and certification. This deals with things like designing the human-machine interface, making sure that the pilot can see outside the flight deck. It deals with external factors like lighting, noise, vibration, and temperature, and what effects does this have on the human. It also deals with workload and with crew errors and many other things. Let's look a little bit at the history of aviation human factors. It actually starts as early as with Leonardo da Vinci, when he first described anthropometrics by drawing the Vitruvian Man. And today we use body measures to optimize pilot controls and equipment. Think about, we need to consider what is the range of users we want to cover. 5th percentile female, for example, all the way to the 95th percentile male. Well, we had the Wright brothers, of course, which really were one of the first who systematically thought how to integrate the human into an aircraft on a flight deck. And today we prioritize the location of controls and displays with respect to the design eye position, which already has been thought of by Orville and Wilbur Wright. Lawrence Berry, another example, the invention of the gyroscope, which made it possible to now also fly an aircraft without any external visual cues. I'm jumping a few now and going ahead to all the way down there, Don Bateman, the invention of the ground proximity warning system, which actually significantly contributed in reducing the risk of control flight into terrain. So these are just some examples of historic aviation human factors work. I talked about the definition of the human factors and ergonomic society on human factors before. But obviously, we also have big regulatory bodies around the world. The big aviation regulator in the United States, the Federal Aviation Administration, and in Europe, the European Union Aviation Safety Administration, and they both have their own definition of what human factors actually means. Not going to read it here, but all of them have some very interesting aspects. In the FAA definition, it talks about it is a multidisciplinary effort, and that is very, very true. Nobody can design a flight deck by themselves. There is a lot of people needed for that. They talk about it's about generating and compiling information about human capabilities and limitations, and then apply that information to our system design. And then we have the definition of EASA. They split it up in human factors and in human performance, where they say, well, human factors focuses on why human beings function the way they do, and human performance is the output of human factors. So it focuses on how human beings do things they do. Nevertheless, all of these definitions have one in common. They are all about understanding the capabilities and the limitations of the human beings. So let's look about these capabilities and limitations of human beings a little bit. And we talked already before, we have the more classic aspects of human factors, the one which I have colored in green here. These are the physical and the physiological factors. Physical factors are those related to the physical properties of our bodies, how big we are, how much we weigh, for example. Where the physiological factors are more like how our body functions, so the mechanics behind it. If we want to understand how we see, how we hear, or how we generate strength. And then we have the ones which I colored in amber here, the psychological factors and the cognitive factors. The psychological factors are the elements of our personality. And the cognitive factors, they really refer to the various functions that represent our awareness. So I give you some example here. Examples for physical and physiological factors that are important for flight deck design. Obviously, anthropometry aspects to determine the reach and the view envelope, to make sure the pilots can reach everything on the flight deck and they can see everything on the flight deck. The strength of the operator, to be able to operate something, motor skills, but also our sensation. And here I'm referring to visual, oral, and tactile sensation. And then there are the psychological and cognitive factors which deal with things like our working memory, long-term memory, human information processing, how we comprehend information, mindset and expectations, how we come to decisions, our ability to respond to certain events in terms of response time or action time, and also alertness, vigilance, and motivation. And then on the other hand, we have the machine, the flight deck. And the flight deck has a lot of properties as well. We have several systems and equipment installed on the flight deck. That could be a traffic collision and avoidance system. That can be our primary flight display. That can be our oxygen masks. These are all systems and equipments. And most of those systems and equipment have an interface to the crew interface. This interface typically consists of controls, displays. Some of these systems may provide alerts. Some of those displays provide information using different colors, red, amber, green, and so on and so forth. We have nowadays a high degree of automation in flight deck, and we need to think about all these systems, all these functions we provide on a flight deck today. How do we allocate those functions? So these are our machine properties. And now let's bring all of this together. What are our flight deck effects? Well, flight deck effects is everything the flight crew can see, hear, or feel. And I made this in green because this is our classical physical and physiological properties. But the flight deck effect is also everything the flight crew must think about. Understand what the automation is doing, why the automation is doing it, what is the automation going to do next, to have situational awareness, to have an appropriate mental model. All these are cognitive capabilities, which I colored here in amber. And then again, all inputs the flight crew can make, for example, with their hands, their feet, or their voice. And these again are classic physical or physiological properties. We can put all of this in a classic stimulus, organism, and response diagram. And then we can say, well, it starts with our sensing, which uses displays. then we have our brain processing the sensed information, and then we respond to it by using controls. These are the flight deck properties in blue, the physical, physiological factors in green, and the psychological and cognitive factors here in amber. Maybe another way of looking at this is the human-machine interaction model. So what you can see on this slide is at the bottom in blue, my machine properties. And on top, we have the human with their physical, physiological capabilities and limitations in green, and the psychological and cognitive capabilities and limitations in amber. And the dashed line represents the interface, the human-machine interface. Very often, people do understand and do consider the classical interfaces very well. The classical interface, the interface between our vision, hearing, and touch, so our senses, and what is displayed on the flight deck, either visually, auditorily, or tactile. Or on the other hand, the interface between our hands or feet and the controls on the flight deck, various switches, touchscreen, for example, or even voice recognition. But what is often forgotten or not paid so much attention to are the more cognitive interfaces. The interface between what the machine is doing, the core processing units, if you want to, the automation, the software that is running on the hardware, and actually the human brain. So that the human understands what the machine is doing and why the machine is doing it by using memory, information processing, and decision making. And on the machine side, storage of data, retrieving data, transmission response, and performing programmed procedures. If we look at today's accident data, then we see that only a few percentage of accidents happen due to system and component failure only. The majority of the accident have some involvement that includes human factors aspects. So around a number is around 80% of accident nowadays have some sort of human factors cause. Let's look at one accident as an example. There are many out there, but let's look at the accident that happened with the Eastern Airlines Flight 401. That was a Lockheed TriStar aircraft. They departed from John F. Kennedy on a flight to Miami. They crashed 18 nautical miles before Miami. But what happened there? During the approach, the crew lowered the landing gear handle, but only 2 out of the 3 gears could be confirmed to be in the down position via the indicators on the flight deck. Unsure of whether the gear or the indicator was at fault, the captain aborted the landing. The flight was directed by ATC to 2,000 feet and was given a course to hold while diagnosing the problem. The autopilot was engaged to hold course and altitude, but the altitude had gradually decayed over a few minutes before the impact. The accident investigation report shows that there was a failure of the flight crew to monitor the instruments during the final minute of the flight. Distraction while dealing with the failure of the nose landing gear position light was a contributing factor, and one of the pilots may have inadvertently bumped the control column, disengaging the autopilot from its altitude hold mode, and this went undetected by the flight crew. So if we apply a classic Swiss cheese model to this accident, then we see the several layers of defenses, and they all had certain holes. That's why at the end of the day, it came to that accident. There was some latent conditions already, like the crew was fatigued because it was the end of the trip. Also because there was no external visual horizon. It was a night flight with a new moon. And then, of course, there was that mechanical failure. The landing gear indicator did not illuminate. Well, then there was a crew error. The autopilot was set incorrectly. and no one recognized the autopilot disconnect warning tones. Consequently, that led to a loss of automation awareness, a loss of terrain awareness, and that no one was flying the aircraft. And the aircraft consequently crashed into the Everglades. So we can look at this and say, well, yes, there was a failure to share the tasks. There was a failure to maintain task priority. There was probably also an over-reliance on automation. There was a failure to recognize the autopilot disconnect, and there was a loss of terrain awareness. But what could be possible solutions here? Implementing a better crew resource management, which focus on one flies the aircraft and the other one investigates the problem. Integrating clear procedures with priority, like aviate first, then navigate, then communicate, then manage systems, and then perform command decisions. Automation philosophy is a very important topic here, where machines and humans work together and do not replace each other. And maybe we can introduce additional barriers. Today available enhanced ground proximity warning systems or even synthetic vision systems, which may have helped to prevent an accident like this. The most important thing, though, is that we need to go away from a person approach that focuses on the errors and violations of the individuals. And I understand it. I mean, blaming individuals is emotionally satisfying and legally convenient. I totally get it, but unfortunately, it doesn't get us nowhere. It simply doesn't solve the problem by saying the pilot made this, and that error. Fallibility is part of the human condition, and we cannot change human condition. Well, we can train pilots, I understand that as well, but even there are limitations. And besides that, training is very expensive. But you can change the conditions in which human works. So we should go more to a system approach, where we trace the causal factors back to the system as a whole. The critical questions we need to ask ourselves is, how and why did the barriers fail? And what can we do to reduce the likelihood of them failing again? David Mindel defines the system as the humans plus the machines. And I think that's a very good way to think about it. By ensuring the user can perform the tasks correctly in the appropriate environment, this will significantly increase safety and system performance. So we should optimize the system and not just the machine. So if we look at this again, first we need to understand the human's capabilities and limitations, the physical, physiological ones, as well as the psychological and cognitive ones. Then, of course, we have in blue how we design the flight deck. How are the controls designed? How are the displays designed? What kind of alerts do we provide? What kind of colors do we use? And those together, the combination of the human's capabilities and limitations and the way the flight deck is designed, this leads us at the end of the day to our system properties, which determine how readable is something, how operable is something, how usable is something, how much workload does something induce, how high is the error rate. This doesn't depend on the human's capabilities and limitations only, and it doesn't depend on the flight deck design only. It depends on the combination. The combination of human plus machine gives us the outcome we want to achieve. The major goals we trying to have in flight deck design can be seen as obviously safety first. We want to create something inherently safe. But at the end of the day, it must also be certifiable. If we can't certify it, then we can't sell it. We don't make any money. We run out of business. It must be easy to use. We want to maximize the system, which means the combination of human plus machine performance, and we want to provide a superior pilot experience. I highlighted certification here in blue, not because it's the most important one, just because this is the one I would like to focus on in the next couple of slides. Flight deck design, as I said before, is a multidisciplinary effort. There is not just one group, the human factors group, doing the flight deck design. Actually, there is a whole of disciplines involved in that. Structural engineers, mechanical engineers, obviously pilots, electrical engineers, certification and airworthiness specialist. Obviously, the customer has a certain influence in the flight deck design as well, and the regulatory authorities, obviously. There are many factors that influence flight deck design. 7 very important ones is the mission of the aircraft. What do you want to do with this aircraft? Is it a fighter jet or is it a commercial aircraft? In what conditions is the aircraft operated? Do you fly with the aircraft in very high altitudes, for example? Or are you flying into day and night or into no icing conditions even? What is your assumed pilot and their characteristics? 5th percentile female to 95th percentile male, for example, would be a classic consideration. But even what language do they speak? Are they fluent in English or not, for example? And then obviously the flight deck design must support the piloting tasks which we were talking about before. Aviate, navigate, communicate, manage systems, and command decision. It must support crew resource management, certification regulations, and operational rules. And baked in all of that, obviously, is human factors and safety. So let's have a deeper look into the certification regulations. On the one and the other side of the Atlantic, we have the FAA with its headquarters in Washington, and we have EASA with their headquarters in Cologne. And what do the certification authorities look for? Some examples include to be able to access everything on the flight deck, reach it and see it. Consistent flight deck philosophy with respect to alerts and the use of colors. An acceptable pilot workload. Minimize and manage crew errors and a predictable system behavior. I highlighted minimize and manage crew errors in blue because I would like to emphasize and focus on this in the next couple of slides. There is actually a regulation specifically for human error. It's regulation 25-1302. Install systems and equipment for the use of by the flight crew. It consists of 4 paragraphs actually, and I'm not going to read them now, but the first 3, they are really about to reduce design contributions to human errors. Basically, do everything you can while you design the flight deck to ensure that the likelihood of a human error is as low as it possibly can be. But also recognize that it will never be 0. There will always be human errors. And that's why there is the 4th subparagraph of 1302, which is all about supporting error management. So first, try to minimize human errors from happening, but recognize that human errors may still happen and then support the management of human errors. But that's not it. 1302 is not the only regulation that deals with human errors. Another very important one is 1309C, which talks about to design to minimize flight crew errors, especially with respect to dealing with failure conditions. And then there's regulation 25-1329 India, which also talks about human errors with respect to the use of flight guidance systems. So you see there is not just one regulation about human errors, there are multiple regulations that needs to be considered. 1302, the regulation 1302 also comes with an advisory circular in Europe that's called acceptable means of compliance. And it actually has one section in there, I believe it's section 3, that talks about what process should be applied while addressing human factors aspects during development and certification. And essentially this process can be thought of a 3-phase process. First, you need to define the scope of your project. Second, you need to define how much work do you actually want to put in there to ensure that you have a good design, the level of scrutiny that is required. And then at the end of the day, the compliance demonstration itself. So let's look at this a little bit. First, about the scope definition. That's about first breaking it up, your design, your entire flight deck in design items. Design items could be functional items such as primary flight information could be a design item. Weather radar could be another design item. Traffic collision and avoidance system could be a design item. And for those design items, you need to look into the crew tasks. In an operational scenario, how is the crew going to use these tasks? And then you analyze all the design items used by the crew members with the aim to identify the necessary controls, the information, and the system behavior that is involved in the crew member action. And then you have to make sure that you document everything that you did. The design to support the ability of the flight crew members to perform the tasks associated with the intended functions needs to be ensured. And then when you have described all your design items, usually on an entire flight deck, that could be something from, depending on how big the aircraft is, anything between 20 to 50 design items maybe. Then you need to analyze these design items with respect to what is the degree of novelty, complexity, and integration. So what does this mean? Well, a design item would be very novel if it has never been used before or certified on an aircraft, a completely new function, a new invention, or you use new procedures or a completely new way how the flight crew interacts with the system. That would make it a very novel system. Complexity here means the complexity from how the pilot perceives the complexity. It doesn't talk so much about how complex the system is in the background, but really how complex it appears to the flight crew by using these systems. And integration, how much integrated this design item is with other design items. And the higher the novelty, the higher the complexity, and the higher the level of integration, the more human factor scrutiny is required. What does this mean? That means you have to do more analysis work. You have to do more evaluations, probably using more pilots. That is what is meant by level of scrutiny. And then we have to show compliance, of course. Showing compliance, what does this even mean? At the end of the day, showing compliance means that we present appropriate evidence to convince the authority of the overwhelming likelihood of our claim that our product is certifiable. Very important, the applicant can only show compliance. It's up to the authority to find compliance, which is the official act by which the authority makes a legal determination that the applicant has demonstrated compliance with the applicable regulations. And for showing compliance, we can use different means. Analysis, ground test, simulator test, or even flight test. I give you one example here that was a project I worked on when I was at Gulfstream, and Honeywell was involved as well. We wrote a paper about this, and these next coming slides are based on this paper. It is a runway overrun awareness and alerting system. You see it in the left corner of this primary flight display. There is a little window showing a runway and showing the stopping points of where the aircraft would stop after landing. So will you stop on the runway, or on the right picture where everything is red, would you overrun the runway, and therefore it's a better idea actually to do an overrun, a go around. Why did we even start a project like this? Well, because there were several reports out there that indicated that there is a problem with runway overruns. This Flight Safety Foundation, for example, found that between 1995 and 2008, there were 431 accidents related to runway overruns, and 712 people died. The European Aviation Safety Agency also found a similar thing in Europe, but also argued that there is an average value of airplane damage estimated to 11 million euros per accident. So there were some really good reasons to develop a runway overrun awareness and alerting system. But in order to fully understand and create a problem statement, the engineers working on that program needed to understand, first of all, what is the aircraft performance? How do deviations from a stable approach, for example, affect the landing distance? What are the effects of aircraft mass, wind, speed, direction, or runway conditions? How do aircraft systems affect the landing performance, for example, the flap position? And what role do system failures play? In addition to that, a deep operational knowledge was required to understand factors such as how approaches are flown, what are stabilized approach criteria, workload during non-precision approaches, as well as energy management and how are go-around decisions made. Once all this was understood, the intended function could be defined, and a design concept was created. The ROAS included graphical indication of predicted aircraft stopping points, which you see on that picture here. It also included visual and oral alerts. The challenge here was that the displayed element must be visually pleasing, but it also must be integrated within existing primary flight displays, because we wanted to offer this as a retrofit solution as well. And it needed to comply, therefore, with the overall already existing flight deck and alerting philosophy. So the proposed solution, obviously, must be also compliant with the applicable regulations. Other challenges were to integrate this new system into the overall flight deck. All systems must work well in normal and abnormal conditions. They must work well together. This requires a flight deck-wide assessment of system requirements, safety analysis, and defining alert prioritizations and inhibitions. Once the design was defined, the human-machine interface requirements needed to be validated. This included various types of analysis. Human error analysis was needed, function allocation analysis was needed, and so on and so forth. But it also included part task and scenario-based evaluations using both simulators and aircraft. Customized operational scenarios needed to be developed to exercise the HF objectives. And for this runway overrun awareness and alerting system, those scenarios included to fly normal approaches, approaches above and below glide slope, fast and slow approaches, extended flares, long landings, approaches with gradually increasing tailwind, of which the flight crew was unaware of, and also approaches with selected system failures, such as one engine inoperative. The applicable regulations had to be identified, and then it needed to be very clear evaluation objectives created. For ROAS, those objectives included assessing aspects of visual and oral alerts to gain the crew's attention, the impact of symbology on cognitive workload, overall impact on go-around decision-making, and many others. The evaluations required the selection of a big variety of methods. For example, Bedford workload scale was used to evaluate flight crew workload. Hayward-Newman scale was used to assess readability of the display. System usability scale was used to determine the overall system usability. Flight technical error analysis were performed. And there were also objective measures, for example, decision-making during the approach. Projects like this, like the development and certification of the runway overrun awareness and alerting systems, require many competencies for human factors engineers. Those competencies go above and beyond human factors knowledge. While human factors is a very important and integral part a very important competency of every flight deck human factors engineer. It's not the only one. As we saw in the example before, good flight deck human factors engineers also need to have a solid understanding of aircraft design and operation, which includes aircraft performance. How do the aircraft system work? What is integrated modular avionic and how does it work? How is the entire flight deck integrated? How is the aircraft operated? And it goes all the way to how are the pilots trained? But a good flight deck human factors engineer also must have a solid understanding of systems engineering. How are avionic systems developed, for example? What is a system safety analysis? What is the typical systems engineering process? How to write interface specifications? How to verify and validate requirements, for example. And as we saw in this presentation as well, certification is a key competency as well. Understanding aircraft certification, operational certifications, how to write human factors certification plans, to identify the appropriate means of compliance, how to write a human factors certification test plan, and so on and so forth, are crucial skills for successful flight deck human factors engineers. However, the industry is facing a shortage of competent flight deck human factors engineers. Me, but all of my peers I'm talking about this topic telling me the same things. We have a really, really hard time hiring qualified flight deck human factors engineers. And this situation is actually getting worse and worse. One reason for this is that we see many of our very valued and experienced flight deck human factors engineers retiring, which leads to a loss of mentors. And on the other hand, we're also seeing an increased global demand of human factors practitioners due to many new companies joining the market. Think about all these new eVTOL startup companies. And on the other hand, there is the problem that the universities around the world do not provide the education that is actually needed to transition directly into flight deck human factors design and certification. There is also a report from the General Aviation Manufacturers Association, GAMA, that was recently published in January this year, which has several recommendations on human factors. And recommendation number 4 actually is exactly along this line. Recommendation number 4 in this GAMA report says that industry should create a formal training course for human factors practitioners on how to incorporate human factors into the overall system development and aircraft certification process. Well, and because of all of that, I joined forces with Kansas University and we developed an aerospace short course program for human factors engineering and civil flight deck design and certification. This is a 35-hour course and it will be offered the first time this year in Seattle from March 17 to March 21. What will this course cover? Well, it will start with giving an introduction to the problems that flight deck human factors engineers face. It will give an introduction and an overview of flight deck human factors problems. It will look into the science, meaning the theoretical models to understand human and machine properties. It will address regulations, the applicable regulations, as well as guidelines and means of compliance. It will look into processes, methods, and procedures for design, analysis, and evaluation and test. It will be rich of technology examples, best and worst examples of human factors engineering applications in flight deck design. It will be very rich of accident analysis with the focus on the human element, and it will provide an extensive literature list, recommended literature for flight deck human factors engineers. The course is structured in 16 chapters, starting with a general introduction, then focusing on human properties, understanding what the capabilities and limitations are of the flight crew with respect to physical, physiological, psychological, and cognitive. And then looking into some important machine properties, such as situation complexity and automation. It will even look into AI a little bit. There will be a dedicated chapter for flight crew alerting and for aircraft handling qualities. And then it will look into the system properties. So when we bring all of this together, what do we need to consider for crew workload, stress and fatigue, flight crew error, situation awareness and decision making? And it will look into engineering properties. So how are we actually doing a good user-centered design? It will give an overview of experiment design for our evaluations, how to collect and analyze the data, and also how to present the data in a report later on to the certification authorities. And it will actually give an overview of human factors planning and executions. In all of these chapters, in every single one, chapter 1 to 16, the key elements included in every single chapters are the theoretical fundamentals of human factors, discussion of aircraft accidents from a human factors point of view. Baked in every single chapter are the regulations with flight deck human factors aspects, flight deck technology examples, design examples, also design and analysis methods, as well as tools that you can use to help you with design and analysis. There will be many exercise assignments and group work assignments, and there is a very rich list of recommended readings. And at the end of the day, there will be review questions provided for each chapter. And that brings me to the end of my short presentation. Again, thank you for having me, and I hope it was interesting, and I'm available for questions now.
Thank you so much, Dr. Konrad. What a wonderful introduction and overview to everything flight deck human factors. I guess I'll start out with a question of my own, and then I'll turn it over to the audience for questions that they might have. I'm a system safety engineer. That's my background. And in the safety assessment process and safety assessment standards, the safety engineers are often allowed to make assumptions about how a pilot is going to react to a particular failure, and then those assumptions get transferred over to flight deck human factors team to confirm them and analyze them. As we move towards systems that are kind of more integrated, more complex, that involve more automation and trade-offs of functions between humans and automation, will these processes need to adapt to kind of better integrate how we do human factors and safety assessment to consider things like combinations of errors and failures and just better, I guess, integrate human factors and safety assessment? Do you think that's going to be necessary? And if so, how do you think that can be done?
Yeah, I think this is absolutely necessary. And by the way, this was also a finding from the Gamma report, which I quoted before. And as a matter of fact, both authorities, the FAA and the EASA, have published standards with respect to that. There is a generic issue paper from the FAA that deals with human factors involvement in functional hazard assessments, and there is a certification memorandum from EASA. I think it's certification memorandum 002, if I'm not mistaken, which also deals with the human factors involvement in functional hazard assessments. And actually both of those, the issue paper and the certification memorandum and the thought process behind it, they will be both covered in my Kansas University course as well. And I think absolutely, yes, that's a very important and topic and is only increasing in importance.
Great, thank you. Does anybody in the audience have questions? I see one question posted in here. In the case of the MAX 8 accidents, what are the major problems related to human factors testing and certification?
So with respect to that, I would also like to refer to the Gamma report, which I was mentioning before. This Gamma report, I believe it's Gamma publication 21, if I'm not mistaken. Could be Gamma publication 22. So either 21 or 22. Actually, what this Gamma Human Factors Flight Tech Working Group did there is they looked into the huge amount of paperwork, documents, reports that were available as a result of the 737 MAX accidents, right? And they analyzed all of this, and there were hundreds of recommendations across all those reports, and some were duplication, some were actually contradicting each other. So this Gamma working group filtered this down, and at the end of the day came out with 15 recommendations that really need to be considered in human factors in the future as a result from the 737 MAX accidents. One of those recommendations was the need for more human factors training in the industry, but another recommendation which I can remember out the top of my head was that the industry needs to develop a methodology for performing human error analysis, for example. Another recommendation was that the industry needs to create a guideline of how to select representative pilots for evaluation and tests. So which pilots should we actually include in simulator evaluation and certification flight testing? So I think it's a great question, and I really would recommend you to read this Gamma report. I think it will give you very, very good answers.
Great. Thank you for the insight. Do we have more questions from the audience?
Well, I can ask one. So there's a series of universities that offer human factors training, some more aviation oriented than others. So if you're to compare with maybe, I don't know, some of the training offered, what is missing currently at university that would be useful to learn when going in the industry?
So the universities do a great job in educating people. Don't misunderstand me. But they're focusing more on the theoretical concepts, which is very important. What I have found when I looked in this paper, which we have published 2 years ago, and the follow-on paper actually last year, what I found when I reviewed the curriculums of various universities across the world, that the certification aspects, for example, they are not really taught. So what does it mean to certify an aircraft? What are the applicable regulations? How do we show compliance to these regulations? What are the means of compliance, for example? Those things are not really taught. And very often the methods that are used in the industry, like how to conduct a human error analysis that is actually later accepted by the authorities for compliance demonstration, not the only means to demonstrate compliance, but as a part of the overall compliance demonstration. So this is one part which is really missing. The other part which is missing is, how to write, for example, a human factors certification plan. What needs to go in there? What needs to be considered? How to write a human factors flight test plan? What needs to go in there? What needs to be considered? So those aspects are typically not taught at university level and really have to be learned on the job training or by teaching yourself. And what we tried with this Kansas University course is not so much to duplicate the academic training which is already provided by the universities, because that's wonderful. It's more like to complement it with those aspects which are not taught so much, like certification and everything that comes with it.
So we have another question here about the course. Can you please confirm that during the course in Seattle, the scenario-based approach for testing will be discussed with some example of application?
Yes, that will be.
All right. We have another question in here about human factors aspects and how they're an integral part of certification and design system used on the flight deck. This person that's asking it is a human factors practitioner working in air traffic control and management. And what amazes them is that there's not a rigorous system in place in that area like we have for the flight deck. Are you familiar with other countries that do have that in place?
So I'm not an expert on air traffic control at all, and my course also will focus specifically on flight deck design. However, what I can say, many of the principles and methods applied for human factors in flight deck design can also be applied in other disciplines. Is it human factors in maintenance or human factors in air traffic control? But I'm not a specialist in that area, so I cannot really talk about that.
Okay. And do you think that human factors research can encourage authorities to modify means of compliance?
So I'm not sure what that means, that question exactly, but I'm trying to answer it. So I think both the FAA and the EASA are constantly contracting university or other research facilities to conduct research on various topics. And usually the results of those research activities are considered by both authorities, and I'm sure by other authorities around the world as well, in updating regulations or advisory circulars or acceptable means of compliance.
Okay.
I have a question, if I may.
Yeah, go ahead.
This is Marek Jaglas. Hi, Gernot. Nice to participate in your very nice presentation. Congratulations. A question: is your Kansas course similar to the University of Stuttgart course, from a few years back, or they are very similar?
So that's a good question. So that started off actually with the course which I'm teaching at the University of Stuttgart. I'm doing this already for 12 years. As you know, Marek, you reviewed my course a while ago and you provided very good feedback. And it is the baseline for the Kansas University course. However, the course at the University of Stuttgart is meant for students. They do their Master of Engineering degree in Aerospace Engineering, and they have a module about human factors. It is more focused on this kind of audience, an academic audience, students pursuing their master degree. For the Kansas University course, I have modified this a little bit, and I'm focusing less on this academic theoretical foundations and more on the applicability and the practical aspects on how do you really do that stuff, right? I can give you an example. At the University of Stuttgart, I would talk about Fitts law and how Fitts law became Fitts law, how it is, right? What is the research behind that? Where in the Kansas University course, I'm just telling you, well, this is Fitts law, and that's how we can apply Fitts law, for example, in the design of touch target sizes on touchscreen controllers. And what does this mean? So there is a slight difference. The University of Stuttgart course is more theoretical. The University of Kansas course is more practical.
Understood. So maybe one more question quickly. You don't have to go into details, but I'm I'm wondering, is anything being done in applying artificial intelligence in human factors, or is it too early to say now? Because I see a certain promise there, and also quite a lot of danger. So is there anything like? I'm sure something is being done, and what's this situation? Could you shortly?
So both the FAA and the EASA, they have roadmaps for artificial intelligence, and the Kansas University course will touch on those roadmaps as well. But at this point, it's quite frankly just a couple of slides. I'm not putting a focus on artificial intelligence at all. I'm not an expert in artificial intelligence either. So I will leave it with a couple of slides and just mentioning, well, yes, that's a topic of growing importance and somebody needs to pay attention to that.
Yeah, it's probably too early to say anything concrete. Okay, thank you very much, Gernot. Good luck.
Absolutely.
Thanks.
And I know we're just about at time. I want to ask one final question here. For the younger members of our technical group or student members who are trying to get into this field, what kind of educational background do you think is best if you want to get into flight deck human factors? Is it an engineering background, a psychology background, somewhere in between? What are your thoughts on that?
All of the above. So I'm a big fan of diversity. If you have the luxury of having a human factors group, in your company, then I would recommend you to make it as diverse as possible, right? It will not help you if you have 10 people and they are all engineers. And it also doesn't help you if you have 10 people and they're all psychologists. I think if you have this diversity, right, you have some bringing the aerospace background in, and then, you know, put a focus on human factors based on that, and the other one coming from a psychology background. Maybe you have some cognitive scientists as well, maybe even some medical doctors, right? So the more diversity you can bring in there in your group in human factors, the more important it is. So I talked before these 4 pillars. You know, you need to know about human factors, about aircraft design and operation, about systems engineering, and about certification. So if you have 4 people in human factors, I would recommend you have 1 expert in each, and everybody is an expert in one area but knows about the other 3 areas. I guess that would be my recommendation.
Great, thank you. That was a good response to that question. We're just about at time, so if you have additional questions, please you can send them either to me or Dr. Konrad. Is there a contact that you can share for people to ask questions? I guess there's a QR code on the screen.
The QR code is for the Kansas University course, but
okay.
I'm not that difficult to find. So you can find me on LinkedIn and you can send me a message. And typically, I'm pretty good in responding.
Great. So as Dr. Konrad said, you can reach out to him. You can also reach out to me through the HFES Aerospace Technical Group forums. My contact information is on there as well, and I can relay any questions if we need. But thank you, Dr. Konrad, for this webinar. Thank you, everybody, for attending, and hopefully you learned something new.
Thank you for having me. It's always an honor to speak at the Human Factors and Economics Society. So I really appreciate the invitation. And thank you, everybody, for listening in. And I wish you all a good day.
All right. Thanks, everyone.
Thank you.
Bye-bye.
Thanks, Gernot.
Bye.
Thank you.